Hello everyone, my name is Ayron Gors and welcome to my Project 5 presentation for CE570. The goals for this week's project I have highlighted above, where we are tasked with defining a vector field on the 3D body of our choosing, and we can go ahead and use the same body that we've been using for the past couple of projects, as well as to compute the divergence of that vector field of our choosing, and to verify the divergence theorem by hand by computing the left-hand side of the divergence theorem and comparing that with the output of our MATLAB result. As you can see in the middle image here, I have defined my vector field of my choosing as it's relatively complicated, but taking the divergence of that vector field, as you can see, is equal to the partial derivative of v1 with respect to x1 plus the partial derivative of v2 with respect to x2 plus the partial derivative of v3 with respect to x3. And you can see that works itself down into a relatively simple but still fairly complicated, as we'll see in the hand checks, of a negative 0.08 plus x2 over h times r2. H and r2 are of course constants of my given body, as well as you can see I have coded in the vector field and scalar field, as you can see in MATLAB in that bottom image. Here we can see my defined body for my silo. I'm still using my silo as we're allowed to use the same shape. And here is the code that defines my hollow cylinder portion of my silo, and I'd just like to highlight some of the added lines of code. As you can see in that very bottom there, you can see I have added this scalar field function as well as this vector field function that are based on my vector field of my choosing and my defined divergence of my vector field. And you can see that I've plugged in the appropriate parameterization for x2 or x1, x2, and x3 into the vector field and scalar field respectively. Moving on, this is the definition of my hollow hemisphere that sits on top of my hollow cylinder. And I just like to highlight a couple added lines of code. Everything else is more or less the same as last week, where I have added a scalar field function and a vector field function. As you can see, the scalar field is just the divergence of my vector field as defined on the right image there. And you can see that I have plugged in the appropriate parameterizations with respect to x1, x2, and x3 in the vector field, as well as x2 for the scalar field as defined in my body parameterization above. So for example, for x2, you can see I have plugged in r times cosine phi. Here, I'd just like to highlight the graphical outputs from MATLAB. It gave me 3 separate plots of my parameterization of my hollow silo, as well as the scalar field, as you can see defined in the bottom there is the divergence of my vector field, as well as my vector field, which functions as a displacement for my silo, where it's once again collapsing realistically. Moving on, I'd like to verify my hand calculations of the left-hand side of the divergence integral expression. And you'll need the parameterization of the hollow cylinder in order to do so. So I have defined it up here above, as well as the volume Jacobian expressed by this equation here, and working out its math comes out to be a value of r. And plugging in the appropriate parameterization of x2 of r times sine theta into my divergence of my vector field, as well as my volume Jacobian into the appropriate expression as seen here, results in an integral expression as shown here, taken with respect to r, theta, and z, and working out all of its math results in a value of negative 45.2389. Similarly with the last slide, this is just highlighting my hand calculations for my hollow hemisphere. As you can see, I've defined my parameterization of my hemisphere above here, and once again we need the volume Jacobian, and it's defined through this expression here, and taking the partial derivatives appropriately and working through its complicated math, it comes down to be an expression of r squared times sine phi, and plugging in all the appropriate parameterizations of my body into the divergence of my vector field, as well as the volume Jacobian, results in this entire expression here, where it is integrated with respect to r, phi, and theta, and working through that complicated mathematical expression using u substitutions and everything comes out to be a value of negative 10.2206. And finally, comparing my MATLAB output with my hand-calculated results, you can see my MATLAB output above for the divergence integrated over the volume of my body as a negative 55.4596, and my hand-calculated results as a negative 55.4595, and the percent error being extremely low for those two values, so I know that my MATLAB code and my math is correct. And it's further verified as being correct as the total flux is also equal to the divergence integrated over my body, as well as the volume of my body and my surface area of my body being equal in previous weeks as defined before. So thank you for watching.